and welcome to your physics final review. If you are in Ms. Jensen's or Mr. Mitchell's class, you might not know me. I'm Mr. Barentine. I'm going to be going through every question on the review sheet. Feel free to skip around within the video and go back and watch things again if it doesn't make sense to you. I'm going to try to explain it. We're going to be showing the sheet itself. So let's get started. The review begins, like all of your tests have begun, with just a basic look at the patterns. So in each section we've looked at slightly different patterns, but they're all the same general patterns that we've used. Linear, quadratic, and inverse. So the three equations, because this asks for the equations, you can't just say linear, quadratic, inverse. Three equations are y equals mx plus b for linear, y equals ax squared for quadratic, and y equals a over x for inverse. So that's the general equations. So in these next three, we're going to have the specific patterns. So where m equals 2 and b equals 0. So we plug those in, y equals 2x plus 0. And then we solve the equation. So I want to see this specific equation first. So then y equals 2 times, what's our x? 5 plus 0 equals 10. No units for this one, although this is probably the only place on the whole test where you don't have units. Quadratic pattern, y equals ax squared. It always helps to rewrite it and then say equals, okay, 2x squared. So when x equals 1, we're going to say 2 times 1 squared. We always square first and then multiply. So this is 2. Not different than that. All right, and then inverse pattern, y equals a over x. So if you want to just start with the general equation, this especially helps in the motion section, which we'll look at in a bit. Equals 3 over x. Always helps to kind of set it up that way. Make sure that you're plugging things in properly, like a Glade plug-in. So if x equals 2, we've got 3 over 2 equals y equals, you can leave it as 3 over 2 or 1.5. Either one works. So I just wanted you to sketch the graphs here. What do the three graphs look like? Linear looks like this, quadratic like this, and inverse like this. So when you're choosing the independent, dependent, and controlled variables, it's an important question to ask yourself is, how does one variable affect the other? Does one variable affect the other? There's almost always going to be a very clear situation where one has to affect the other. The independent affects the dependent. We can kind of do a little effects. Independent affects dependent. Controlled variables stay the same because we can't change more than one thing at a time and experiment on it and get good results. So, how does the time a ball is rolled affect how far it is rolled? Well, ask yourself, does the distance it rolls affect how long it rolled for? No, that doesn't actually make sense. It has to be the time that it rolls affecting the distance. So, time and distance. And then controlled variables, you have to use a little bit of logic, but sometimes the control variable is kind of in there. So like ball, right? It's got to be the same ball. Maybe the same force of the push would be another good one there. There's a few different options there. As long as you list two controlled variables, I'm happy with that. So what about number of review questions you answer versus how well you do? Well, would how well you do affect how many review questions you answered? No, it can't go backwards like this. So we want to see how many review questions you answer affects your grade on the final exam. Very clear order there. So questions answered. Exam grade. And there's a few different versions of this. You don't have the exact phrasing correct, as long as you got the ideas down. So what are some controls? If we were going to do this experiment, we would need to do the same exam each time. We would need to maybe have the same person, although that would be kind of tricky, but it is I answer, so same person. But that does make this kind of a difficult experiment to actually conduct, but an easy experiment to pick the IV, DV, and controls for. Okay, and then we need to say how does the amount of likes I get on a picture depend on what time I post it. So if you do this wrong initially and you go, okay, likes time, which is not correct, we would be saying that the number of likes affects the time that you posted it, which would be implying that if I get 80 likes, all of a sudden I posted it at 4 in the afternoon instead of 4 in the morning. But that doesn't make any sense. So if you write it out, just ask yourself, does this affect this? It's a nice little check. So it's not this, it's time affecting the likes. And then in control variables, well, if we're going to actually test this, we would need to make sure it's the same picture, right? A picture of your cat does not get the same number of likes as a picture of your lunch. We would want this to be the same person, so like maybe same number of followers, or even the same person posting to their followers to see how that goes. And I've actually heard of people changing what time they post on their Instagram because it gets more likes at different times. So anyway, we got to say, how does the IV affect the DV? All right, so when we're graphing a data set for linear and we find the equation of the best fit line, we use that Algebra 1 skill. y2 minus y1 equals m times x2 minus x1, right? This is how you find the slope of the line. You could also just say find slope and y-intercept. And then it would go into y equals mx plus b, because that's the equation for a linear line. What's the crucial difference between linear and inverse? You got to get this. Linear, when one variable goes up, the other goes up. And we want to be specific when you're saying the answer. So this, we're talking about it generally, but if I was talking about like force versus acceleration and mass versus acceleration, I would want to say when force goes up, the acceleration goes up. This is linear. But inverse, and this is the crucial difference, inverse, when one variable goes up, for example, when mass goes up, what happens to acceleration? Well, it goes down. Crucial difference in the comparison. And then linear and quadratic, well, this is still linear, but quadratic, we actually have one variable going up, the other goes way up. That's the crucial difference. That's why it's a curved line, is because it starts off slow, but it's going to go up even faster. Whereas linear, if it starts off like this, it would only go like this. And so linear, the quadratic, the y variable goes up faster in a quadratic situation. To review the lab report guidelines, I want to actually go through kind of a little example lab really quick. So for example, here's a wild guess question. How far will a ball drop in 10 seconds? So when we're building the research question, we want to say, what is the relationship between the two variables in the wild guess question? How long the ball is dropped, 10 seconds, and how far it goes. But we can't say 10 seconds in the research because we're going to find lots of different distances and times so we can find the connection between the two. So I'm going to guess that it's going to go 40 meters. Why not? So then I have to pick out my independent and dependent variable from the research question. We've practiced this a couple times, but let's do it once more. Which one's going to affect the other? So will the distance that it has dropped affect how long it has dropped for? No, it can't go further, and that makes the time change, right? The time will be different, but it doesn't make it change, which affects the other. Hint, time is almost always the independent variable because it's hard to change it. And then dependent is, of course, the distance that it's fallen. And if you used a different phrasing here, like how far it goes, that's fine. You've said the same idea. I'm just kind of shortening it for time. So then we take our independent and dependent variables and we put them in the hypothesis graph. Dependent always goes in the y-axis, independent in the x. And then to make the hypothesis, we think, okay, if it has a really small time, will the distance be large or small? Well, I think if it's not very long, then it won't be very much distance. And if it goes longer, it'll be more distance. And if it goes longer, it'll be more distance. So I think this is going to be a linear relationship. So then in words, I would just say that when time goes up, distance goes up. Really good hypothesis would say because of gravity or something like that. So then we need controlled variables. What do we keep the same in this situation? Well, the ball is right there, right? Ball, that's simple. We also want to have, like, we're going to be dropping a bunch of balls and seeing how long it takes them to go different distances, how far they go in different times. So what do we need to keep the same? Well, we want the same ball, right? We would want to use the same air, which is kind of a funny thing, but you wouldn't want to do some of the experiments inside and some of the experiments outside. So this is another way we pick controlled variables. We want same
weather conditions, right? We wouldn't want to do one on a foggy day and another on a sunny day, because that would mean the air was a little bit different, and that might affect our data. So our procedure, we would want to draw it. We're going to drop a ball, right? Multiple different times, and we're going to time how long it takes. And you want to label your procedure drawing with, okay, we're going to time it, and then we want distance, right? So we're going to label that as well, distance. So it's very clear that we're timing how long it goes different distances. And in the procedure, I want you to say, we're going to drop the ball different distances from different heights and time each. Because then you'll get actual data. So here on the study guide is the data and graph for this situation. And I want you to, now we're going, so here's the data. If you were given data, you would have to copy it down into this section. Make sure that you label your columns, right? We would want to say, okay, we're going to take distances and times. And distance is in meters and time is in seconds, right? We want to label our units in our columns as well. So then we come here and we go into Logger Pro. I'm sorry this is so hard to read. What it says is D equals AT squared plus BT plus C. And then it says A equals 5.00, B equals 0, and C equals 0. So when we're getting the equation, we want to always plug these A, B, and C's in and get the most specific possible equation. So this can go really simply. You can think about your template, but basically you just have to say, my graph, right, from my line of best fit, from my graphed data, I know that the relationship between the two variables, so this is evidence right here. That's all you have to say. Evidence. And I don't want to write out this whole conclusion, but I know that the relationship between these two variables has to be, and I want to say the relationship between distance and time. When you say relationship, I want you to say the two variables, the specific variables. Is, all right, so it's this curve, so it must be quadratic. With the math equation of, and this is where we fill in the most specific version that we know. We want to say D equals 5t squared plus 0 plus 0, right? So we're already more than halfway done with the conclusion. Now we just need the prediction and the confidence. So for the prediction, we go back to our wild guess question. This is critical. We go back to our wild guess question. How far will a ball drop in 10 seconds? I don't care about your wild guess answer, because we're going to find a way better answer using the data. And so using the data, we know that D equals 5t squared. This is a relationship between these two variables. So I can plug in any t here and find the D. So I'm going to plug in my 10 seconds from the beginning. D equals 5 times 10 squared, which is 5 times 100, which is 500. And it's distance, so it must be in meters, because here in my data, our distance was in meters. So 500 meters. So in the conclusion, you want to say, in 10 seconds, I predict it will fall 500 meters. And then your confidence is based on two things. Confidence is based on how well does the line of best fit, which this one fits really well, and is your prediction near, within, or outside the measured data range? So our data range goes to 5 seconds, and we're predicting for 10 seconds. So that's outside the data range. So I would say moderate confidence. The way you could get high confidence is if the data fits perfectly and we were looking at like 3.5 seconds, because that's right in the middle of our data range. We'd probably be really, really good on that. All right, so then down here, I'm not going to go through this so specifically because it's kind of everything we did up here. Evidence means proof. It means where did you get this information? We have to say where we get the information. 3 possible relationships, linear, quadratic, and inverse. Mathematical equation, we get it from the graph. And then we solve for the prediction, plug it in. Plug it in, plug it in. Going to get GLADE all over this problem. And then what two factors? Best fit line, it's right up here, best fit line, and whether the prediction is near, within, or outside the measured data range.